Hi, I'm Tommaso, PhD at Graz University of Technology.
And I'm Daniel, also a PhD at the Graz University of Technology.
Welcome to Bridge the Gap, the physics-oriented podcast,
in which we give insights into various research topics and the life of scientists.
And by the way, if you want to contact us, you can drop a line to our email address bridgethegap@tugraz.at. Hey Daniel.
Hey Tommaso.
Do you know how many phases of matter there are?
In principle 4 and I don't know, maybe some other special ones?
Well, what if I told you there's yet another phase of matter? Ever heard about the mozzarella phase?
I suppose that one is exclusively taught at Italian universities.
Well, maybe the greatest experts in this particularly tasty field are Italians. Who knows?
I must acknowledge, I certainly am not. Anyways, we asked some students and colleagues of ours what they knew about mozzarella phase and phase transitions in general.
And that is what they had to say.
A phase transition usually describes matter transitioning into another form, for example, ice melting or water evaporating. Overall, there are 4 main states of matter which it can transition into, with number 4 being plasma, which is often forgotten. But I've never heard of the mozzarella phase. Maybe it has something to do with nuclear pasta, but I don't know.
Phase transition should be a state between 2 states, so like the start and end phase or state, and the phase transition is something in between to go from state A to state B. And I haven't heard about mozzarella phase, but I'd guess this is somewhere in between liquid and solid.
Okay, what do we mean by phase transition? It's something about spaghetti, I think, like how long it takes for them to cook in a way that they are especially yummy afterwards.
Totally agree with her.
And ever heard about the mozzarella phase? I think it has something to do with pizza, but I'm not 100% sure what.
How long you have to cook the pizza so the mozzarella is the best.
That sounds about right.
Yeah.
So today on the podcast we have Ivan Di Terlizzi. Ivan is a researcher at the Max Planck Institute for Physics of Complex Systems in Dresden. And we're very excited to have him because he's an Ig Nobel laureate. So Ivan, welcome to the show. And can you introduce yourself? Tell us about your studies, field of expertise. Stage is yours.
Hi, Tommaso. Hi, Daniel. Thank you very much for your invitation. So, as you anticipated, I'm a researcher in Dresden. I'm a postdoctoral researcher, and I'm Italian. And I studied in Italy, in Padova, to be precise, where I did my bachelor, master, and PhD under the supervision of Professor Marco Baiesi. During my PhD, I mostly focused on statistical physics, which is a little bit the topic also that in which the physics of Cacio and Pepe can be framed. And but to be a little bit more specific, I focused on stochastic thermodynamics, which is a very exciting field, I would say, where basically we focus on studying the thermodynamics of microscopic and mesoscopic systems. If you want to describe the thermodynamic features of these systems at a mesoscopic scale, you need stochasticity, so randomness, probability theory. And this is what I focused during my PhD and also the time on which I'm focusing here now.
Maybe to start with some very basic things, so our listeners get a bit of a basic understanding, let's say, right? Can you explain to us what a phase transition is in physics? And could you give us some everyday examples of this?
Yes, sure. With great pleasure, because phase transitions are one of the favorite topics of a physicist in general, and in particular for statistical physicists like I am. Let's say this is the classical example of what is an emergent phenomenon. An emergent phenomenon is something that indeed emerges from a system composed by many small elements that behave collectively in a different way, like which is very different compared to what you would expect by looking at single components. To try to explain this a little bit better, maybe I can again try to give a little bit more an introduction to what statistical physics actually is about. And the classical example of this is gases. So gases are something that classically is described, for example, by the state equation of perfect gases. So pressure times volume equal or proportional to temperature. This result is very fundamental. I think everybody studies it at school, and it was first described at the mid 1800s when thermodynamics was born. And this was an empirical observation. There have been experiments about it, but nobody could actually explain why this equation holds. And here comes in play the father of statistical physics, which is Ludwig von Boltzmann. And he managed to describe the gases as an ensemble or collection of atoms that interact in a certain way and that collectively give rise to this macroscopic observable, which are pressure, volume, and whatever. Temperature is a parameter, so it's not an observable. Which means, again, you have a macroscopic phenomenon, pressure, which comes from the microscopic description of atoms, which, by the way, it's very important. This is the very first time that somebody was talking about atoms in a scientific way. Nobody believed him, and poor Boltzmann committed suicide. We needed Einstein to prove that actually matter is made by atoms. So this is one of the many incredible results that Einstein had in 1905 alongside the special relativity. But again, I'm talking too much. So to make a long story short, when you have a lot of small components that interact together, there are these emergent phenomena. And the most, let's say, trivial example is water. Water is something made of water molecules, so hydrogen and 2 hydrogens and 1 oxygen. The molecule has a very strong dipole, and so molecules can interact with this dipole interaction. Now, when you cool water below 0 degrees, water freezes, and you have a phase transition. And what does it mean, phase transition? You have a macroscopic observable, in this case called order parameter, which abruptly changes. So in the case of water, actually defining an order parameter is not so simple, but you can think it about really something that measures the order. When you have water, molecules are going around and there is a thermal motion and a lot of things happen. At a certain point below this critical temperature, because like phase transition are always characterized by critical points, critical lines, critical stuff in general. Once you go below this critical temperature, instead of having this very chaotic motion, you have a crystalline structure. So there is order. So instead of having translational invariance, which you have in liquid water, in ice, you don't have translational invariance because every point is different. You have a invariance which is given by the lattice. So phase transition is something where macroscopically something changes. And to do another example, there is magnetization. So if you have a magnet, there is a temperature called the Curie temperature, above which the magnet is not magnetic anymore. Below this temperature, the magnet is magnetic. What does it mean? That so in a lot of materials, like I think iron or other metals, you have these domains where atoms are oriented in the same way. These are, I think they are called Weiss domains. Above the Curie temperature, these Weiss domains, they're all oriented randomly. So like the net magnetic field is 0 because everything is random. Below a certain temperature, let's say the free energy of the system is such that the system is happier if all magnetic domains are aligned. And when they are aligned, there is a magnetic field that appears. And why am I talking about these two things? Because like water, is a first order phase transition, which means below 0 degrees, like immediately you have order. So like this transition is very discontinuous. Like first you have water, then you have ice. Instead, in the case of magnets, like below the Curie temperature, you see like continuously like the appearance of this magnetic field. And then once you go down in temperature, this field becomes stronger and stronger. But this is a continuous transition. So the first one is a first order phase transition. In case of magnets, instead, you don't have like latent heat. Everything is continuous. But another very important thing is that at critical points, you really see some very nice mathematical features like correlation functions diverging, and all like susceptibilities diverging. Maybe these details I won't discuss. But after I moved here to the Max Planck Institute, I came in contact with, let's say, a more biologically driven environment in terms of physics applied to biology. And also, just to anticipate a little bit the topic on which we are going to focus at the end of this discussion, there is this very exciting field called phase separation. So phase separation is a physical phenomenon which basically tries to explain, and manages to explain actually, why water and oil do not mix with a mathematical framework. So this applies, for example, to the physics of emulsions, so kitchen as well. But this is actually not the prime, like people are not mainly focused on this. But this is actually very interesting also from a biological point of view, because you have to imagine that the cell is composed by organelles like ribosomes, the nucleus, and many others. And all these organelles were typically regarded to as being all with a membrane, in the sense that you have like a region in space which is divided by the rest of the cell by a membrane. And but what was found is that there are many organelles that have no membrane. And this makes sense from let's call it an evolutionary point of view, because like cells, very often they happen to be in a situation where they have to act fast, like an infection or some kind of stress. So maybe they need some specific protein to be produced for a specific task. And they need, let's say, a factory for these proteins. So they need an organelle. But building a membrane is very complicated. So what the cells do, and this is like a very important work from the beginning of the 2000s, which really like blasted the field to the moon, where they showed that cells can form these membraneless organelles by tuning some internal parameters like temperature or acidity or concentration of whatever component to trigger the phase separation of some components separated from the rest of the cell by forming these membraneless organelles that then do stuff like producing some specific proteins. So this is a field that I was not an expert of, and I'm still not an expert of, but I've been talking about this so much in the last year that now I know something about it, which by the way is also relevant to the formation of beta amyloid plaques in the brain, which leads to the Alzheimer disease. So like aggregation of proteins is something like of interest nowadays. And we thought that Cacio Pepe is the perfect example, a little bit lighter, to discuss this kind of physics.
This was really a super nice introduction, actually, even more.
Long, but...
No, that was really amazing. What would you say that in your field, the definition of equilibrium versus non-equilibrium phase transition is? So is there a crystal clear definition for that?
The most important quantity to describe a system at equilibrium is a free energy. And the system will act in such a way to minimize the free energy. So imagine like a free energy that has a quadratic term plus a quartic term. So ax squared plus bx to the fourth. For some parameters of a and b, you will have something that has a minimum at 0. So, and imagine that the x variable is your order parameter. So X is the order parameter. The free energy as a function of the order parameter has the shape that I just told you. And for the parameters that we chose, which are, for example, temperature or something different, the minimum of the free energy is at 0, which means that the system will do in such a way that the order parameter minimizes the free energy. In particular case, order parameter equal to 0. Now imagine that some parameters are tuned, so temperature changes, some other condition change, and the shape of the free energy is not anymore something that has a minimum in 0, but has two minima, one at plus minus something. So in this case, the system will choose one of the two minima in which the order parameter is different from 0, but the free energy is minimized. So this is the concept. You have a free energy at equilibrium, you can always define it, and you can, and the system will minimize it. And depending on the parameters, the minimum will be at 0 or a value different from 0. Once this happens, you have a phase transition. The non-equilibrium doesn't have a free energy, and everything is much more complicated. So there is no unique recipe to detect a non-equilibrium phase transition. And because in non-equilibrium, there is no general mathematical theory of non-equilibrium. So every case is very specific. You have to invent yourself an order parameter. You have to look at some mathematical signatures of phase transitions, like diverging correlations, diverging susceptibilities, where the susceptibility is how the system responds to a external perturbation. But this is all very mathematical.
Then maybe one more sort of basic question before we continue to your paper, actually. Could you tell us what a phase diagram is and what it is used for?
So like, to make a long story short, is a plot at the end of the day, a diagram where you can say, okay, if I am at this temperature, this pressure, what is the state of my system? Here it's water, here it's gas, here it's very weird ice, here coexistence. And you have a lot of critical lines which define these phase transitions. And then you have this triple critical point, I think it's the name, where you have the coexistence of many different states. So again, water is a very complicated system.
So, and talking about your recent paper about Pasta Cacio Pepe.
I was waiting for it.
Yeah, which is me too. I mean, as Italian, I kind of resonate with this. So it's a famous Italian dish, right? It means pasta with cheese and pepper. So
Exactly.
yes, in this paper you try to lay down the theoretical foundations in order to make a very nice creamy sauce, in order not to have clumps in the cheese component. So can you tell us about this work a little bit, and then also why? Why did you choose to investigate pasta?
First, disclaimer, the group of people that work on this, we were mainly theorists. So I'm like, let's say I'm a little bit ashamed to say that it's much more an experimental work compared to a theoretical work. So we are Italian physicists in Germany. I have a confession to say I'm half German. But still, I lived in Italy, so like you miss Italy, and you have these Italian friends, and you have colleagues from all over the world. And in winter it's cold, and restaurants are expensive. So what do? You cook some Italian dishes at home, and you share it with your friends. Now, I really like to cook for a lot of people. I have very big pans. We cook carbonara, we cook puttanesca, risotto, and but of course, like, people know about cacio e pepe, so people were asking, why don't you do cacio e pepe? Like, we see it on Instagram, we see it there, we see it there. And like, my answer was, look, I can cook cacio e pepe. I think I'm a pretty good cook. But even if I do it for one or two people, sometimes the pasta is well, it will be edible, but for sure suboptimal. Like, this is not great for my pride. But then we said, okay, no, we have to do it properly. Like, if everybody has to come here, like, we have to do it properly. So we discussed a little bit, and then we talked to our supreme boss here, and we said, look, do you think this is a stupid idea? And he said, no, this is very interesting. And then we said, but can you pay us the cheese? And he said, no, I don't think I can pay the cheese. But yeah, we bought the cheese. And then we reunited it in my home. And we made a lab out of my kitchen. It's very funny to see how the first photo of a cacio e pepe sample was of the 11th September 2024. And 1 year and 1 week after, we won the Ig Nobel Prize. So for 1 week, it wasn't like super, super precise. We said, okay, what we need here, the main aim is to construct a phase diagram of the cacio e pepe sauce. So task number 1, find some relevant thermodynamic parameters. So for sure you have temperature, because what we know is that the problem of cacio e pepe is that the proteins change the nature when the temperature goes above 65 degrees. And this is important because, like, if you think about milk, for example, so milk is an emulsion of water and fat, and is kept together by casein, which is a protein which binds both fat and water. One is like one has an electric charge, and the other one has no electric charges. So again, water is electrically charged because of the dipole. Fat acids, which are not charged. So like these emulsifiers, they bind both because they have an amphiphilic head and an amphiphilic. My God, I don't remember the exact English words, but you understood what I meant, right? You have this thing that keeps everything together. So once the temperature goes above 65 degrees, caseins and other proteins as well, they change their conformation. So they don't act as emulsifiers anymore. And even worse, they start to aggregate. So not only they don't like, so before they don't like to stay together and they help stabilizing the mixture. After that, they don't like to stabilize the mixture and they want to aggregate. So it's the worst. And above 65 degrees, this happens. So of course, this thing must be characterized by temperature. Also because when you're cooking, it's all about heat and temperature. So this was like a natural choice. And then the other thermodynamic variables, we pinpointed the 2. The first one is the relative concentration of proteins inside water. And this is important because usually in phase separation, you look at concentration because concentration is something that triggers transitions. But there is even more complicated than what I said before. In this case, I would say for the sake of simplicity and the time, you just believe me that this is a relevant quantity. But more practically, probably, the important thing is the amount of starch. So how much starch you have in your sauce. And everybody knows, probably not everybody, but let's say a lot of Italians know that pasta water is very important to achieve great sauces because it binds and it thickens the sauce and pasta risottata is also a thing nowadays. But while in the case of, for example, aglio e olio, while in the case of aglio e olio, starch actually helps bind the sauce, and that's it. Also a little bit an emulsifier, but like it's not such a disaster if you don't use enough starch. In the case of cacio e pepe, people already knew, mostly nonnas and chefs, that if you use enough starch, actually the sauce is much more stable. And like we tried to like condense all this knowledge, mostly taken from YouTube, I have to say, into something that sounded more rigorous from a scientific point of view. And to do so, we did this apparatus where we could like systematically explore different concentrations of cheese with respect to water, with respect to starch and stuff like that. And by checking the state of the sauce at different temperatures. So another important thing that I would like to say is that, of course, if you want to exactly test the amount of starch that you have in your sauce, you cannot simply rely on pasta water because like who knows how much starch is in the pasta water. Again, we were doing everything in our kitchen, so like we could not do opacity tests or something like this. It was much more easy to gelatinize some starch like maizena or potato starch. In German, it's Speisestärke. And we bought Speisestärke and we measured the amount of starch we wanted to use. We gelatinized it in water, which, by the way, is another very nice phase transition, which you look interests. So like I will talk a little bit about it because it's a very interesting phase transition. So you have starch in a granulated form and like you have these polymers which are all entangled and very dry. Then you put it in water and you heat up water. And the thermal energy helps breaks these granules, these micelles, it's called. The technical word is micelle. So like these polymers start to detach from the micelle and they absorb water and they become elongated, they stiffen. And then at a certain point, all these polymers are free in water and they are free to bind and they form a network. And if you try, because we have a recipe, of course, but we will talk about this later. And if you try to do the gel, it is very incredible how you heat up the water and first it's opaque and and like with a normal viscosity. And then at a certain point, you really see like, poof, everything becomes much more transparent and much more viscous. Because like you had this transition from a disordered state to a network state, which is kind of solid, but it's a weird state, but it's a different state, so the phase transition. So this thing, apparently we have an explanation why it helps to stabilize the sauce is because it really like does a mechanical caging of the proteins, which cannot mechanically touch themselves anymore because like there is these starch polymers that impede physically the attachment of these proteins. So yeah, I already spoiled a little bit the result. What we found is that if you use enough starch, like this disastrous aggregation that you sometimes see in some realization of the dish does not happen anymore. And instead, below a critical quantity of starch, which is 1% of with respect to the cheese mass. So like if you have 100 grams of cheese, if you use less than 1 gram of starch, above a certain temperature, you have this phase transition from a homogeneous sauce. I think it's figure 2, if you look at it. You get to what we like, what we called the mozzarella phase. So it's like a new state of matter, which we like to joke about that it's the only case in nature where a mozzarella is a bad thing. And this was very funny because like we were calling it mozzarella phase, and then at a certain point we were writing the paper and we said, do we actually say it? I said, yeah, let's put the mozzarella phase. People really liked it apparently. So like
They do.
And then like to conclude, like we did this phase diagram where we found a little bit more, we had a practical message, which means use enough starch, pre-stabilize the sauce in such a way that when you heat it up, meaning that you put it in contact with the pasta, it does not, it's like stable enough with respect to temperature perturbations that you don't end up in the mozzarella phase. Then we said, okay, let us do something a little bit more technical. And we varied the concentration of, we fixed a certain amount of starch and we varied the water concentration. And without going too much into detail, we found this curve, which really looks like something that is observed in other systems that do phase separation, which is called a binodal curve, which is a curve where two states coexist, like the triple point. In the triple point, you have more states coexisting. So here we have another critical line where you have separated, not separated, phases that coexist together. And this is characterized by an equilibrium of chemical potential and free energy forces, if I'm not mistaken. So like there is a coexistence of forces because there is coexistence of phases because of equilibrium of forces. But again, very technical. It's not that it's interesting, but like probably too long to explain. So we found this binodal curve and we try to describe it with some theory, which again is an attempt, nice, but like still an attempt. Oh, very important thing that I forgot. Sorry, as you see, I like to talk a lot. How do you characterize the state of the system? Again, we were looking at phase transitions, so we wanted to characterize this with an order parameter. Again, what is the order parameter here? Like with our instruments, the only thing that we could do was to take photos of the sauces, which were analyzed through photos of sauce in a Petri dish. By the way, it was a stolen Petri dish from our lab. And we asked the permission afterward. They said, okay, yeah, don't worry. Like they're not so expensive. They're plastic ones. So we took photos. And then like this colleague of mine, who is like also my flatmate now, Vincenzo, he's great at analyzing photos. Like he's super, super skilled. So we were also very lucky that we were 8 people and we had a combination of skills. So this is why also I think the paper at the end of the day ended up being so nice, because like there was the person that knew about phase separation, the one that could cook well, the one who could sequence data, and the one who could write well. So like it was a good combination. So like we took photos and then we said, okay, what happens when you make a wrong cacio e pepe? You have this mozzarella, but this is characterized by these elongated stripes of cheese, no? In Italian, it's called filatura. So we said, okay, a good way to characterize the state of the sauce is at looking at clumps. We approximate them as ellipses, and we look at the major axis, so how elongated they are. And we said, okay, this is our sides, the clump sides. And then we say, okay, for each sample, we take the average sides. And the average size is our order parameter. And if you look at the phase diagram that I showed you, the one with the starch, where you see the mozzarella phase, you have these values which vary between, I think, 2 millimeters and 7 millimeters, something like this. No, from 2 to 5, sorry. And then you have the mozzarella phase, where the order parameter is the size of the Petri dish. So again, a diverging order parameter, which sounds a little bit, phase transition. So then we put everything together. We wrote a nice story. We said, okay, why don't we put also a scientific recipe? Maybe people will like it. People mostly looked only at the scientific recipe. I can also say something like a lot of people said we invented the recipe. This is not true. So the recipe was already proposed by a Michelin star chef, Luciano Monosilio, which was also our only non-scientific reference, which was like we referenced a YouTube video. We said, okay, we saw this video, we got the inspiration from that. Nobody said this, of course. So some people said, oh, the recipe is not new, already somebody did it. Of course, because that was not the point. We wanted to characterize the phase transitions, the physics behind, and then also the recipe, and which, by the way, we used a lot lately. I cooked more than 20 kilos of cacio e pepe after the paper came out. Some of our friends did the blood test, and the cholesterol was out of... But yeah, like we had to do it, and it never failed. Also, and this to connect a little bit to what I said before, so the recipe that we propose is for 2 people, 300 grams of pasta, 200 grams of cheese, 5 grams of starch, 150 grams of water, do this, and do that. You read the recipe maybe, because let's make it more about physics rather than the recipe. But the important thing is that now you can scale it up very easily. And this is what we call the thermodynamic limit. Because we did the experiments with 50 grams of cheese, and then you take a spoon, and then you say, yeah, but we are talking about phase transition, statistical physics. We need the thermodynamic limit. So these are these big pans of 2 kilograms of pasta where everything still holds.
You did not just use starch to stabilize the sauce, but also something else. I forgot the name.
Trisodium citrate.
Precisely. Could you tell us about this? Because you say that it reduces the clump size, right?
Yes, no, it's actually incredible. So like, again, I'm not chemist. I got some of this information from generative AI tools, just not to say trivially ChatGPT. But then we looked also for the papers, of course. Like the first thing, let's see. So trisodium citrate is a salt made from citrate ion and from sodium. So the citrate ion has this characteristic of chelating calcium. Calcium is contained in the casein, like, you drink milk because, it's rich of calcium. It's in the caseins. Because like caseins are micelles, so a lot of proteins all together held together by calcium. And when you denature them, what we believe is true, what happens is that these calcium ions are exposed and then they bind together. So this is why the casein aggregate and do these clumps. So if you have something that has a certain affinity to calcium, like the citrate ion, you basically imagine like two proteins that have some patches that want to stick together, but then you put something on them and they cannot stick together anymore. So it has this very chemical effect. So at a certain point, when you have enough sodium citrate, you don't have an aggregation at all. So you really have zero clumps. With starch, because the thing is more mechanical, again, like the network, like the mechanical impeding of proteins coming together, you still have small clumps. They are fine. The important thing is that you don't have the catastrophic phase transition, but that's fine. For sodium citrate, it's perfect, like super smooth. It's like we are very careful at saying that it is a first order phase transition because, as I told you before, phase transitions are mathematically precise phenomena that are characterized by divergence of susceptibilities, correlation functions, latent heat. We cannot measure this. So we talk about a very sharp transition which resembles a first order phase transition. But we are not sure at all that this is a first order phase transition. But it's very sharp, much sharper than in the case of starch. Now, so this is the chemical nature of this emulsifying agent. It's apparently used a lot in the food industry because it works very well. So of course we are not the one who discovered this. We only put together a lot of knowledge that was known here and there. We put a little bit of Italianity, like salt by, and people liked it. We are very happy about it. But we basically, well, maybe the experimental protocol was new. So this is why I say these are more experimental work rather than a theoretical work. But yeah, like this, it works flawlessly. But from a chemical point of view, this salt is made of citrate ion, which comes from citric acid. Citric acid is a weak acid. So like the corresponding basis is also weak, but is not so weak. Instead, the sodium ion comes from hydroxyic sodium. I'm not a chemist, but like NaOH is a super strong basis. So like the Na ion is a super weak acid. So like in general, this salt is slightly basic. So it changes the flavor of the sauce. And in particular, I have to say, well, we did some tests, of course, like to see which one is better. Like starch doesn't change the flavor at all. Also, it's technically an ingredient because you use pasta water. So you have starch. In this way, you're just using cornstarch, which has the same identical molecules, maybe in a slightly different proportion between amylopectin and another one of which I don't remember the name. Again, I'm no chemist. I'm sorry for that. But like with sodium citrate, you are really using something that is not traditional, which is not a problem to me. Again, probably it's the German half here speaking that like tradition, yeah, it's great, but like it's not something that should be seen as a tradition. Probably somebody is gonna hate me for that. I apologize. But in the case of sodium citrate, aside from this tradition problem, which again it's maybe a problem, it's basic, and the flavor is different. So we are all very careful of saying you use 100% pecorino. Let's say 30% of parmesan if you really want, but already not too close to Rome. And it's all about like feeling very good pecorino, but so you really want to feel the cheese. And citric acid a little bit, the trisodium citrate a little bit spoils this.
So after this very tasty discussion, we can say, are you cooking up something, some new works? Can we expect something at least as tasty as this one from you?
We have, look, of course, like after all this story, we were all galvanized. Like we said, okay, now our career path is clear, at least like a parallel career path. But like the first very trivial extension is to look at gricia. So, like this typical Roman workflow where you have first cacio e pepe, then you use cacio e pepe and guanciale, you have gricia. And then if you add tomato, you have amatriciana, and if you add egg, you have carbonara. So the first step would be to see what happens if you add fat. So the empirical observation, at least from my point of view, is that doing gricia is easier. It doesn't happen having this mozzarella phase is much more difficult. But it's in a certain sense counterintuitive if you think about it. Like mixtures of water and oil are more unstable rather than water and water alone, of course, doesn't make sense. But yeah, like water and oil don't like to stay together. So why adding something that is fat could help? We don't know. Maybe it's not true. Maybe I just didn't do enough gricia, and like I did it a couple of times, it turned out well, and I was happy. I did much more cacio e pepe, and sometimes it didn't go out well, so I said, okay, yeah, cacio e pepe is more difficult. But I'm not the only one saying this. So like, let's see what's the role of fat as an emulsifier. So this is one idea, and the other ones are secret. Sorry for that.
No, that was a very, very nice and inspiring conversation. Thank you, Ivan.
Thank you guys for sticking with me until the end. Thank you again.
Thanks for listening.
And hear you next time.
And by the way,
if you want to contact us, just send a mail to bridgethegap@tugraz.at.